Yeah, so I'm going to talk about some work I did with these great collaborators recently on trying to find transferable jailbreaks for VLMs. So just for context, we have adversarial attacks for image classifiers, well studied, of course. An interesting fact about these is that these often transfer across models. Like you can train an adversarial attack on one image classifier, transfer it to a different model, and it still works. GCG, also, I'm sure well known in this room. You can create adversarial text attacks, and the really interesting finding from this paper was that these transferred from being trained on Vicuña to attacking successfully ChatGPT, Gemini, Claude, and so on. Also, adversarial attacks on VLMs are now increasingly well studied. This great image hijacks paper showed, doing a gradient-based image jailbreak for a variety of different VLMs. However, the transferability of these attacks between VLM models has not previously been well studied, and that's what we looked into. And the reason you might care about this is gradient-based methods are very powerful. If you have white box access to a model, you can basically just always use gradient-based methods to find an adversarial jailbreak that will succeed. But if you require white box access, obviously it's a much less relevant attack, particularly for most powerful models are behind APIs. We don't have white box access. But if you can transfer successfully, then suddenly this is a very concerning attack vector that cloud providers need to be aware of. So I assume people mostly know VLMs, but just quickly for context, you have a pre-trained LLM off the shelf, usually pre-trained vision encoder, add a projection layer, do a little bit of training, and you have a VLM. And this makes them very easy to train even in the open source community. So there are many VLMs that follow this kind of architecture in the open source community, such as Lava. So what we did is just a very standard sort of gradient-based jailbreaking method. For VLMs, we have a generated data set of many harmful prompts and responses. We start with some randomly initialized image. We combine this with a prompt, give it to the VLM, and these VLMs, all being safety trained, will refuse to do the bad thing. And then we take the cross-entropy loss between the actual response, which was a refusal, and the known harmful response that we expect from this prompt. And then we just backprop through the model to update the image to minimize the loss. And this works very well. When you do this, you can basically very quickly create an image that will jailbreak your target VLM across all of the prompts in your data set and anything you really care to throw at it across any different topic. So you basically just get a image that will cause the VLM to just no longer have any refusal behavior. It will just help you do whatever bad thing you ask it to do. Yeah, and it's also very easy to create a image that jailbreaks multiple VLMs at the same time. And you simply do this by optimizing the image against an ensemble of many different VLMs. So if you take 8 VLMs, optimize the image against all 8 of them in parallel, you'll have an image that jailbreaks all 8 of these VLMs. And none of this is too surprising. This is all kind of what we expected based on prior work. And then the thing that we also expected to work was that we could then transfer to a new VLM outside of this ensemble and successfully jailbreak that. But in fact, we could not do this. We found this was basically, at least in every case we tried, we found this just to be impossible. We could train, or we could optimize an image that would break 8 VLMs. The 8 VLMs in the ensemble could be super different from each other, and then transferring or attempting to transfer that image to jailbreak any other VLM that was not in the ensemble just wouldn't work at all. It would be indistinguishable from the original random image in terms of its effect on attack success rate. So this is pretty surprising. We really didn't expect this to be the case. From prior work, we just totally thought that it would be easy to transfer this, image classifiers you can transfer, GCG you can transfer. But for some reason, in VLMs, it seems quite difficult. There is one limited case where we found success. If you're transferring between different checkpoints of the same training run, you can successfully transfer, and the amount of transfer you get decreases as the checkpoints get farther apart. And this also works if you have identical models where one of them differs by having been fine-tuned on some additional data. So we have some suspicion now that there's some relationship between the similarity of the models that you're trying to transfer between and the ease of transfer. This is not like super well characterized at this point, but yeah, similarity helps. So yeah, just to summarize, it's sort of unsurprisingly very easy to create image jailbreaks for VLMs. It's very hard to transfer them to black box models, like much harder than we might have anticipated, but it is possible to transfer between very similar models. And actually just recently there was this paper from Meta where they looked at image jailbreaks for early fusion VLMs, which is just a different VLM architecture. And they also found that while it's easy to create image jailbreaks, that they were not able to transfer jailbreaks between different chameleon models. So this is a surprising and interesting finding, I think. And I think there's a bunch of like clear next research directions that hopefully some people in this room might be interested in. And if so, please talk to me later. I'd be happy to chat about any of these. But basically, I think it's like just quite puzzling why transfer doesn't work in this case, but does work in other cases. Transfer in general of such attacks is sort of an interesting thing to study, but it's quite currently quite unknown why this doesn't work well in VLMs. And then, yeah, there's like a lot of work that could be done just to like try and make the transfer work. Now we have some success with the similar models. We now have some like foothold in attacking this problem. We can start, tweaking experimental details and increasing the amount of transfer we get. And there's a lot of work that can be done to sort of characterize what it is about two different models that makes transfer succeed or fail. Like we know that when models are very similar, we can get transfer, but what exactly needs to be similar, like which aspects of the model, what can we vary and still have transfer succeed? That's all pretty unknown. So I think there's a lot of like interesting low-hanging fruit here. And yeah, happy to chat about it after. Thanks.